When we look at benzene, if you look at it from the top, that's sort of what benzene looks like. Okay? And this is much different than what we have in cyclohexane. As a matter of fact, if you go and try to build this molecule, then you'll find that it's really, really easy to build in comparison to cyclohexane as far as the bond angles are concerned. If we look at that from the side, this is sort of what it looks like. Okay? So, just as we were talking before about hybridization and delocalization, can you see that the p orbitals up top almost kind of make a circle? They almost even join. And the same thing happens to the bottom. And that's really what's happening when we have this delocalization that happens. One other note before I go any further. You have to watch some of your model kits. This particular model kit is such that we have a little bit different structure, even though this is the same color as the other tetrahedral structure. So just be careful where you pull out those carbons. So what we find in benzene is that that molecule is so incredibly stable. It actually got people interested in a special classification of molecules called those that are aromatic. So aromatic compounds. This is something that's incredibly stable, or particularly stable set of cyclic structures that are due to delocalizations, and they have a very large amount of delocalization energy. In other words, the amount of energy that it releases by allowing the molecule to delocalize its electrons is actually quite significant. We call that an aromatic compound. Now, when I was in college, I thought that it must smell really, really good if it was called aromatic, and that was the difference between an aromatic compound and a non-aromatic compound, and I was totally wrong. They just happened to name it that because the first molecule they were looking at actually smelled good or something to that degree. So they may or may not smell. We just call it that, okay? In order to fit the criteria for being an aromatic compound, these atoms need to be in a ring. That's the first criteria. And each atom must have an unhybridized p orbital. Here's what I mean by that. They have to have an open orbital where there's p. In other words, they need to at least have sp2 hybridization. They can have sp, although that's rarely found in a ring, but sp2 is much more common, okay? That also means that if they have a positive charge on a particular atom, that is also indicative of an open p orbital. They have to be planar, and they have to follow what's known as Huckel's rule. There's a lot of complication on Huckel's rule, so I'm going to simplify this for you. Huckel's rule tells you how many electrons can be present to give rise to an aromatic compound, and the rule is 4n plus 2, where n is any whole number. It has absolutely nothing to do with how many carbons are in that ring. That was a confusion that I, again, had when I was in undergrad. But it's easier for me to just think of it as we need an odd number of pair of electrons, whether they be pi electrons or lone electrons. Either one of those works just fine. So I kind of drew out what we have here in benzene. So this is my really bad drawing of what this really is, okay? In that if you have benzene, we've got 3 double bonds. That means that every single one of those atoms has an open p orbital. And so I just drew that out here. And you want to practice doing that too, because that's helpful to sort of be able to visualize that in your mind a little bit. But when we look at it from a realistic perspective, if you imagine again, we've got a hamburger in the middle, and Paula Deen has put donuts above and below that hamburger to make it a yummy sandwich. And that yumminess is what we call aromatic, okay? So an aromatic compound is a particularly stable compound. If anywhere in that ring you have an sp3 carbon, in other words, one that doesn't have a positive charge, it doesn't have lone electrons, it's not got a pi bond to it, then that means that the open p orbital is now interrupted. And you can have delocalization in the other parts of that ring, but the entire cyclic structure is considered to be not aromatic. Because, again, you have to have a ring in order for it to be classified as aromatic. If a compound has open p orbitals, it's planar and it's cyclic, but it has an even number of lone pairs or pi electrons, in other words, it doesn't follow Huckel's rule, then we consider that anti-aromatic. Anti-aromatic compounds are basically the exact opposite, if you will, of an aromatic compound, in that these are very unstable. They're inherently unstable. So if we consider the wave functions of electrons, there are things that just maybe might sound right. So like if you're into music, harmony that sounds beautiful together, we might consider that sort of like an aromatic type of situation. And like a sharp or a little bit of a flat key, one that kind of makes your skin crawl just by hearing it, that's what an anti-aromatic compound sort of is like. The wave function just doesn't work well together. It's a particularly unstable compound because it wants to get out of that situation. So, anti means that you're not following Huckel's rule. An easier way, again, to see this is that you have an even number pair of electrons. So some examples, and I will get to these two momentarily. Benzene will be an aromatic compound. This guy's an aromatic compound. He's aromatic because there's an open p orbital here as well, and we have one pair of electrons. Here, this is also aromatic. Note that yes, you have 5 carbons, but again, it has nothing to do with the amount of carbons, it has to do with the number of electrons. Everybody has an open p orbital, and we have 3 pairs of electrons, or 6 electrons. Again, I'm going to come back to this in just a minute. These compounds are not aromatic. The reason why here is because you have an sp3 carbon right there. Same thing here, and same thing here. Other compounds that may be not aromatic are large rings that are simply not planar. And finally we have anti-aromatic compounds. So these are things with an even number of electrons, but otherwise fit into the aromatic composition. Here we have 2 pairs of electrons. Same thing here. Okay, so particularly you see in the cyclopropene, that we have aromatic, not aromatic, and anti-aromatic compounds simply by changing the charge or changing the nature of one of the compounds in there. Okay, so now let's talk about these two situations. I'm going to write that out again. Obviously, this side of the compound is aromatic. Okay. We rather have to figure out when we're going to count these lone pair of electrons and when we're simply not. And there's a reason why we count what we count when we count it. I hope that made sense. If we look at a benzene ring and we insert a nitrogen with a lone pair of electrons. Okay, well, make sure you can see this. This nitrogen is part of a 5-membered ring. He's involved in a double bond. He's also sp2 hybridization, where there's 1 bond, 2 bond, and then this is their 3rd bond. If you want to consider a 3rd bond, it's not really a bond, obviously, but it is a 3rd object, shall we say. lone pair of electrons. How you actually would put that into a ring. Oh. I'll probably have to edit this, so sorry if it takes a minute. It's just like that. Okay. So that is very much an aromatic compound. But notice I didn't put anything in here. The third thing that's coming out, instead of being a bond, is actually another sp2 orbital with just electrons in it. This is going perpendicular to the plane of where the benzene is. Well, one of the unstated things that we really refer to in aromaticity is that in order to be aromatic and share that delocalized area, they have to be flat and in the same plane. Electrons must be flat and in the same plane. This is perpendicular to that plane. You can only have one set of electrons from any atom that are parallel with all the other atoms within that ring. Therefore, these are the electrons that count. And these electrons we don't count when we're talking about Huckel's rule, or we're talking about electron pairs. So these still exist, but this is the one we count, and we don't count this one. Okay. Now this situation is actually quite different. In this case, we have a nitrogen that has 1, 2, 3 bonds. So I'm going to change the model here. And we can have on this nitrogen 1, 2, 3 bonds. Notice that I have kept this p orbital as an unhybridized p orbital. And the reason for that is, look, it delocalizes. It's nice and pretty. Well, the reason why this particular one does not go through an sp3 hybridization is simply because it's more stable not to. Remember, the reason why you even get hybridization of orbitals is due to a lower energy, or a lower energy state. By keeping this particular pair of electrons out of an sp3 orbital configuration and keeping it into an unhybridized state, that actually allows this molecule to gain energy through delocalization of the overall molecule. Because in this case you would have 1, 2, 3, 4, 5 pairs of electrons that would count towards Huckel's rule. And so therefore that would make it an aromatic compound. So think of it this way. Because of the fact that these electrons refuse to be part of an sp3 hybridization, and instead that nitrogen says, okay, I'm going to keep one p orbital open, that allows an overall stability of this molecule to increase. And it allows you to just have 5 pairs of electrons that would count in that configuration of the aromatic compound. And that's exactly why these electrons do not show up as an sp3 hybridization. Thank you very much.